Welcome to chapter 10. So chapter 10 is about correlation and regression. We actually introduced the idea of a linear correlation and the linear correlation coefficient a little bit earlier in our work, but we're going to look at it more fully now in chapter 10. And there are 5 sections in chapter 10, but our class is only going to look at the first 2, and then we're going to move on to chapter 11. So sections 3, 4, and 5 will not be covered. They're not on any of the assignments, so we don't have to worry about them. 10.1 is about correlation, and then 10.2 is about linear regression. So what's the key concept of correlation? We introduce the linear correlation coefficient R. Again, we did introduce it previously, but we're introducing it here. And it's a number that measures how well paired sample data fit a straight line pattern when graphed. So again, when you have pairs of data values, then you can form points with X and Y being the paired values for each data pair. And then you plot those points on a graph, and then you could see if the points seem to go in sort of a linear pattern. And we'll look at a lot of examples of these graphs in this introduction to try to develop our judgment as to whether there appears to be a linear correlation between data sets when they have matched pairs. The other thing to mention is that matched pairs is what we were just discussing at the end of chapter 9, or at least our final section in 9.3, when we worked with matched pairs of data. And when we were working with matched pairs of data, we talked about sort of the difference in those matched pairs. But now we're talking about whether there seems to be a linear relationship between those values. Like, if I know the first value, I can use a linear equation to predict what the matched value with that would be. So we are working with paired data again, but now we're going beyond just comparing the data values. We're actually looking to see if there's a linear correlation between the two. We use the sample of paired data to find the value of R, and then we use R to decide whether there's a linear correlation between the two variables. That's not strictly true, even though it helps. So we're going to talk about R and the R value a lot, but you may recall that R is a number between -1 and 1. And if it's very close to 0, that's a stronger indication of a lack of a linear relationship between the two. And the closer R becomes to being a 1 or a -1, the more powerful the argument that the data have a linear correlation, seem to match a line. But this is a mathematical and graphical measurement. And as we will see, it's possible to have a fairly high R value, meaning getting up there close to 1, when you actually do not have a linear correlation, because there's some other correlation instead. And we'll see that in the upcoming graphs. So it says we consider only linear relationships, which means that when graphed in a scatter plot, the points approximate a straight line pattern. Then we discuss methods for conducting a formal hypothesis test. So that's a much newer concept, a hypothesis test. We didn't have that when we talked about linear correlation before. That can be used to decide whether there is a linear correlation between all population values for the two variables. All right, so that's a lot. And as you can see, there's 59 slides in this set. We will not get through all of them, but we are going to skip over all of the ugly formula slides, since we'll be using technology to do those calculations instead. So let's get into it. All right, so we begin with the definition of a correlation. A correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable, meaning that you can imagine that one of the variable values is somewhat predictive of what you'll get with the other one. as opposed to no association, that the values are completely independent from each other. So this kind of goes back to the idea we looked at before about whether two variables seem to be totally independent from each other. If the values of variables are completely independent, you could still match up pairs, but which one you got for one variable wouldn't seem to have any predictive value of which one you got from the other because they're independent. Well, now we're looking at having those matched pairs and trying to see if there is a dependence or not. And then if so, is it linear or not? So then a linear correlation, more specifically, that exists between two variables when there is a correlation and the plotted points of paired data result in a pattern that can be approximated by a straight line. So let's look at some graphs. So remember, every time we have a point now on a scatter plot graph, the point represents a pair of data values, one value for the x variable and one value for the y variable. Thinking of our earlier examples, maybe one value was a measurement from the left hand and the other value was the measurement from the right hand of the same individual. And when you pair those data together, you plot 1 point of that left and right hand value pairing. So each green spot on our graph here is both an x and a y value. And what we're looking to see here is if, for example, the size of the x value helps give some indication of the size of the y value. And so in this example here, they're showing us there's a R value that was calculated of 0.859. And again, R values are going to be only numbers between -1 and 1, maybe close to 0, maybe close to a positive or -1. So in this case, this is getting up there kind of closer to a +1. And they're going to say there is a positive linear correlation here. So why is there a linear correlation? So for example, you want to imagine as x gets bigger, and I'm seeing the x value sort of move in this direction, does that correspond to y value getting bigger? That would be a positive linear correlation. And one of the ways to see this is that there's no points down here and there's no points up here. And what that's suggesting, for example, in the x direction, that as the x value gets bigger, the y value is not able to stay low. That as x gets bigger, it forces the y values to get bigger. And that's why there's a correlation. And we call this linear in this case because even though it's not a nice clean line here, you can kind of imagine that there's sort of a line down the middle that would kind of suggest what's going on. And so that's a simple starting example for us to see. And what you would see is if those green points didn't deviate from the line that I've drawn down the middle as much as they do, then the R value would get closer to 1. If they were spread out even more, the R value would start to fall. And if there was really all kinds of values in here and also in here, instead of just around the line, the R value might actually get pretty close to 0. Now, we don't have to have a super high degree of accuracy when seeing these patterns here, and the slides they show us and the conclusions we draw from those slides will give us a sense of how to use judgment when deciding if there's a linear correlation or not. So let's look at another one. So in this case, they do look even more tightly close to a linear relationship. But instead of going up and to the right, it's going down as you go to the right. We can still imagine there's sort of a line through the middle here, and that the data values do seem to adhere fairly close to this linear pattern. But the reason now we say that this has a negative linear correlation is because the increase in the value of x now with the data causes a decrease in the value of y. As x gets bigger, y gets smaller. And we also do see these very large gaps here and here. There's really nothing deviating very far from the line. And so the linear correlation is quite strong here. And you can see that by looking at the value itself, because it's quite close to -1. Oops. So because y stays between -1 and 1, you'll never get a value below -1, like -2. You'll never get a value bigger than 1, like 3 or 4, or even 1.1. The formulaic way that R is calculated will guarantee that the values always are between -1 and +1. And so it's really just about how close are they to one of the ones, or instead is R kind of in the middle and closer to 0. And again, being closer to 1 or -1 suggests a stronger linear correlation. And then a smaller sized R value that's kind of closer to 0 suggests a weak or lack of a linear correlation between x and y. And if it's getting close to a +1, then you have a positive linear correlation. If it's getting close to -1, then you have a negative linear correlation. Questions, comments, discussions about this graph here? All right, so they've shown us a couple of nice graphs of a scatter plots that had a demonstration of a linear correlation, both positive and negative. So what does it look like when they do not have a linear correlation? Well, here's the simplest example, basically just a cloud of data. And so this is a nice demonstration of basically no correlation between the two. Because when x gets bigger or smaller, that doesn't seem to have any impact on whether y gets bigger or smaller. As x is getting bigger, there's plenty of small and large y values corresponding to large x values. And similarly, as x gets smaller, that doesn't seem to have a strong impact on what kind of a y value you can get either, because there are small x values with small y values, and there are small x values with large y values, and everything in between. And so what we see is that when there's no correlation here, R is close to 0. And in this case, if you think of like R, since R has an absolute value always between 0 and 1, you could almost think of it as a percentage, either negative or positive percentage. So here you're talking about, an R value with 7.4%. That's a low percentage value. So as it describes no distinct pattern, suggesting really no correlation between x and y at all. They're completely randomly independent from each other. Now, our final example, 4 out of 4, is when there does seem to be a correlation between x and y, but it's not a straight line correlation. It's not linear. And they describe it here as a non-linear relationship. So in this case, we got an R value of around 33%. It's not very strong. It's closer to 0 than it is to 1 or -1. So that is saying that in terms of a linear relationship, there's none really, or a very, very weak one. But you can see there seems to be a pretty strong relationship in the data here. Instead, in this case, it just kind of looks more like a parabola. And so actually, x is very strongly predictive of what you'll get for y. When you know what x is, it tells you a lot about what you should get for y. But it just doesn't follow a straight line pattern. For example, some of the time as x is getting bigger, so is y. But then some of the time as x is getting bigger, y is decreasing in value. And the fact that that changes and doesn't stay the same is when the relationship is nonlinear. because curves don't always go in one direction. They might go up for a while, then go down somewhere else. So there's a very strong relationship here. It's just not linear. Therefore, the linear correlation coefficient R can be showing, help see that because it's a smaller value. But sometimes you'll have a curve, like imagine you have a curve that was like this, but a little bit more like a line. Like if I have a relationship that looks like this, that's clearly a curve, but the curve isn't as far from a line as this big upside down U is in the example they showed. So in this case, I would have nonlinear as well, but actually the R value might be a little bit higher because those points don't deviate too far from a line. You could imagine I could have a line through the points pattern, and the points don't deviate all that far from the line, but the way they show a nonlinear relationship ends up meaning it's not a line. So we cannot only look at the R value to determine whether we have a linear correlation. We need to look at the R value, but we also need to look at a scatter plot at the graph as well of the data. And you will see problems in our homework and discussions about how both things are important when deciding whether there's a linear correlation in the data or not. Both the graph as well as the R value are important. So I do want to point out, you will need to make some judgments in some of the problems, and graphing will be part of that when deciding on a linear correlation or not. Pardon me while I'm munching. So keep that in mind, that even though it's not just about using StatCrunch to get values here, the graphs aren't just clarifying ideas. We actually have to be able to look at graphs and make judgments. So we want that skill developed here. So there's the 4 graphs they just showed us. We use the linear correlation coefficient R, which is a number that measures the strength of the linear association between the 2 variables. And they have a nice range of examples here. So now let's define that a little bit more carefully. Linear correlation coefficient R measures the strength of the line correlation between the paired quantities X and Y in a sample. So imagine you have a line that runs through the data, and that's the best line you could use to predict to stay close to the data as possible. The R value is kind of like how close the points are to that line. So think of it as a distance away versus close or not. But also simultaneously, whether you have sort of an upward or downward correlation, meaning does an increase in X cause an increase in Y? That would be a positive. Or does an increase in X cause a decrease in Y? That would be a negative correlation. Both of those are quantified in the calculation of the R linear correlation coefficient. So objective, determine whether there's a linear correlation between 2 variables. So they're going to introduce a bunch of notation that they're going to use in formulas, which I'm going to mainly ignore. I will point out that N is still the number of pairs of data, which was what we used in 9.3 when we had matched pairs. And there'll just be one N value because since all the pairs are matched, you're not going to have different numbers of X's than you do of Y's. They're all matched together. So in this case, you can think of N as the number of points on the scatter plot, and each point coming from a matched pair of data values. But there's going to be X's and, well, they're setting up the notation here in order to do formulas, which we're not going to use. So I'm going to move forward through this. Calculating and interpreting the linear correlation coefficient. Notation for the linear correlation coefficient. So the R is the linear correlation coefficient for a sample. And as in most of our examples we've looked at, when we then look at a letter to represent the population versus the sample, they will typically use a Greek letter. But in this case, it just looks like a P, which we used for population proportion, but the symbol actually should be looked more like this. So let me write it. I don't think the slide, somebody put this in on the slide, but it's not really correct. It should look more like this. And I know that still kind of looks like a P, but I think it's pronounced row. I'm going to put R-O-E. And it's a Greek letter. It's like a small R as a Greek letter. And so when they're using the row symbol, that's kind of like the mu symbol or the sigma symbol when they're talking about the population versus just talking about the sample. So the rho would be the linear correlation coefficient for the entire population of point values, of matched data value pairs. Whereas the R is the one you get from your sample. So as usual, we have some requirements we need to meet in order for the calculations that we do to be valid. Given any collection of sample paired quantitative data, each of the data needs to be quantitative numerical so we can plot on a graph. The linear correlation coefficient R can always be computed, and this is important. The linear correlation coefficient R can always be computed. Given any set of data values with numerical data in these pairs, we can always calculate an R. That doesn't mean there's a linear correlation. And the thing to remember is R, if you get a value that's close to 0, it's actually evidence that there's no linear correlation at all. So R can always be calculated, and it just doesn't mean there's a linear correlation until you judge the value of R along with the pattern of a scatter plot. So the following requirements should be satisfied when using sample paired data to make a conclusion about a linear correlation in the corresponding population. So to draw a conclusion about the population from your sample, fulfill these requirements. Number one, as usual, we need to have a simple random sample. Otherwise, the results, if the data was biased in its collection, then the results will be biased as well. But then it says visual examination of the scatter plot must confirm that the points approximate a straight line pattern. So this is saying you have to look at the graph. No matter what R tells you, you need to look at the graph and see a straight line pattern. So that's where the judgment of a graph is a requirement in order to work with this. And then finally, because the results can be strongly affected by the presence of any outliers, which they'll do some problems and show us to illustrate, any outliers must be removed if they are known to be errors. So when you're collecting data, it's quite possible that mistakes are made, measurements are made inaccurately, people report things inaccurately. And so sometimes you get some wayward value that you're like, really, that just seems hard to believe. And so if you can confirm there's errors, then you need to really make sure to remove those because they can really mess up your R calculations. R calculations are very sensitive to outliers. And so because of that, we have to be very careful when calculating R. We have to be very careful to consider if we think there's errors or outliers in the data. Now, being an outlier doesn't mean there's an error. It could be that it's way over there because there is not a good linear correlation, and that sometimes you have these values that are not close to a line, and that should be taken into account. But those are the ones that'll most affect the calculations, and so you should double check whether there's errors there or not. The effects of any other outliers should be considered by calculating R with and without the outliers included, so that you could say, for example, well, we have this one value that's really throwing off our R, and it may not be correct. So we're going to check on that. Here's what R would be without it. Here's what R would be with it if it is actually valid. So that you keep in mind that one crazy value might really throw off your R value a lot. And then it states specifically requirements 2 and 3 above are simplified attempts at checking this formal requirement. The pairs of X and Y data must have a bivariate normal distribution. That's 2 and 3 are basically how you're trying to determine that. But you don't need to know that word. Okay, formula number 1, let's skip that. Good format for calculations. No, it's not. Formula number 2, good format for understanding. No, I really don't think that helps our understanding. Calculating and interpreting the linear correlation coefficient, rounding it. So in general, there's a rule that you would round R to 3 decimal places. But as we're doing problems in my stat lab, of course, it'll always tell you where to round things off. So now let's talk about the idea of a claim and things like that. Interpreting the linear correlation coefficient using a p-value from technology to interpret R. Use the p-value and significance level as follows. If the p-value is below the significance level, that supports the claim of a linear correlation. If the p-value is greater than the significance level, that does not support the claim of a linear correlation. So what does the p-value mean? Why is this the way this is set up? I don't think the next slide is that helpful. So let me interpret this like our null and alternative hypothesis. So we are doing a claim about rho, which is the linear correlation coefficient for the entire population. And as usual, our null hypothesis will be a claim that the variable involved is equality, has equality, and we're going to, in this case, set it equal to 0. And what does that mean? No correlation. No linear correlation. I'm going to put that in actually. So remember, if R is close to 0 or rho is close to 0, that's saying there's no linear correlation, that if there's any relationship between the data, it's not close to a line at all. And so then the alternative to that, if we want the alternative hypothesis to represent the idea that there is some sort of a linear correlation, well, as soon as you leave 0, either heading toward +1 or toward -1, you're establishing a linear correlation. And the farther you are from 0 and the closer you are to a ±1, the stronger the linear correlation there is. And so the alternative hypothesis of just there being a linear correlation can be summed by saying that rho is not equal to 0. And the farther it's not equal to 0, meaning the higher the significance level you have to be away from 0, the stronger the linear correlation. So I'm going to put exists linear correlation. And so if we see the null and alternative hypothesis this way, then this description here fits in with our normal idea of performing a hypothesis test. If the p is low, the null must go, and we support the alternative hypothesis. So that's why they're saying if the p-value is below the significance level, that supports the claim of a linear correlation because that is the alternative hypothesis here. And if the p-value is not below the significance level, we fail to reject the null. The null is that there's no linear correlation. And if we're not rejecting that, that does not support the claim of a linear correlation, that a linear correlation exists. So that's why these are framed the way they are, but think of it in terms of the rho value. And then remember that when rho equals 0, that's no linear correlation. When rho is far away from 0, closer to 1 or -1, that's when there exists a linear correlation. And so when the p is low, linear correlation exists in this case. It supports the claim of linear correlation. If the p is low, the null must go, no correlation must go, so correlation exists. I know that's a little confusing. All right, so having said that, there's slide 2. They say we could use a table to interpret R, and there is an R table here that some of the problems give us like critical values for R, in which we don't really have a tool in StatCrunch to do that. So there'll be a couple of problems in your homework probably where you need to use the table that they give you, but it's super, super simple. I think I already did an example of one, but maybe we'll take a look at that. But in general, there's correlation if the absolute value of R, because R could be heading toward a 1 or a -1, is greater than the critical value. So again, the R value with not the rho, but the R value is the test statistic in this case. So this is the test statistic. The R value is like the T value or the Z value or the P value, right? It's the test statistic when you're testing for linear correlation. And so you can have an R value that's the critical value for R, meaning how big a number you need in order to get into the critical region and conclude that there's a linear correlation. This is a two-tailed test because you could be close to 1 or close to -1. You could be away from 0 in either direction. And that's why there's going to be two sort of critical values for R, but they're showing the absolute value is larger than some positive critical value number that they're using there. And so using the critical value method, then if that's the case, there's sufficient evidence to support the claim of linear correlation. But if you don't surpass the critical value of R at the confidence significance level that's set for you, then there would be failure to support that claim, insufficient evidence. So it's newer letters, and for whatever reason, they're changing the terminology here a little bit, but it's in line logically with everything we've been doing so far. So now let's look at properties of this R value, like we did with chi-square distributions and T distributions and things like that. As I've been discussing and reiterating, the value of R is between -1 and 1 inclusive always. And if all values of either variable are converted to a different scale, the value of R does not change. So this is really helpful to keep in mind, because R value is just about how far you are away from the line, whether you're using a scale that's in inches or feet or miles if you're measuring distance, or seconds or minutes or days if you're measuring time. If you change the scale, but then calculate R using that new scale, you're still going to get the exact same R value. And so it's a nice property to point out about R, that R does not change even if you change the scale that you're using to measure the data values. And it says the value of R is not affected by the choice of X or Y. So which one you call X and which one you call Y will not matter in terms of how far the data points are from the line that best goes down the middle. If I flip an X and Y, the line will get flipped, the points will get flipped, but their proximity or closeness to the line will not be affected, and therefore R will not change based on that. All right, so that's some properties of R. R measures the strength of a linear relationship. It is not designed to measure the strength of a relationship that is not linear. So it's only a measurement of how close the points are to a straight line, nothing else. And as it mentioned earlier, R is very sensitive to outliers in the sense that a single outlier could dramatically change its value. You remember in those graphs, and I had some points that look like this, I was like, notice there's nothing down here and there's nothing up there. That really helped us confirm the idea that there was a linear relationship. Well, so if you all of a sudden stick a point down here or a couple of points in those areas, that can really throw off your R value and bring it down closer to 0. And so R is very sensitive to outliers of that type. So we have an example using technology, which is probably the one we'll want to look at, and then maybe we'll try to see if we can hop over and do an example from the homework set. So the table lists 5 paired data values. Use technology to find the value of the correlation coefficient R for the data. So notice this is a very small sample, only 5 pairs of data values. And they have something to do with chocolate and Nobel, which I believe stands for Nobel Peace Prize or something like that. But nonetheless, these are just 5 pairs of data values. You could toss them into StatCrunch or other technology and get some information. So they're saying, look, we dumped those 5 data values in, and here's different things that we were shown. So here's our little StatCrunch example here, but they all give you basically the same R value of 0.9795 rounded to 3 decimals. And it just says that the value of R will be automatically calculated with software or a calculator. Thank you. And then it says, here's an example using a formula where it takes them 3 slides to do that. And so I'll just cruise through those because we don't want to do that. Look at that. This is how they're warming up to use their formula. And then they get to punch in a bunch of stuff. Aren't you happy now that we're using some technology instead? Ugh. And of course, they get the same result. So now it says finding R using a formula off of 10.2. It says it's easier to understand how R works. If we go through all of this nasty work, we can get z-scores for X and z-score for Y and make this table. And you can see I'm just moving through this because I want to make sure that I've told you not to worry about all of that. If you are somehow intrigued by the formulas and they help your understanding, that's great. But I want to alleviate the fear that most students start to develop or the panic when they see these crazy formulas and remind us that we are not emphasizing that, or we're de-emphasizing that in favor of interpreting the StatCrunch results. All right, so let's take a quick peek at this example about whether there's a linear correlation and see how far we can get before bailing on the slides. All right, it says using the value of R equals 0.801, so it's at about 80% for 23 pairs of data shown in the next slide, and a significance level of 5%. Is there sufficient evidence to support a claim that there is a linear correlation between chocolate consumption and the numbers of Nobel laureates? So they're using the same, they're using chocolate and Nobel, so apparently these paired values are trying to see if there's a relationship between how much chocolate a country consumes and how many Nobel laureates that country creates. Like eating chocolate makes people win more Nobel laureates. Doesn't sound like you'd think there's a relationship there, but who knows? Maybe there's something to it. Now notice there is an R value of around 80%. So you could say, well, that's certainly closer to 1 than it is to 0. But that's not the way we're going to go. It's not going to be that simple. We're going to have an alpha level, in this case, a significance level of 5%, and we're going to have to use the math to make judgments. And the best basic idea is do we think that if there was no linear correlation, there could still be a decent chance that our R value would come out the way it did? It's going to go back to the definition of the p-value again. What is the probability that if there was the null hypothesis was true, that there was no linear correlation, that our sample would come out with this R value? And unless that p-value falls below 5%, if you could get an R value of 0.8, even if there was no linear correlation more than 5% of the time, then we can't rely on this as evidence that there is a linear correlation. It needs to be stronger than that. But if getting an R value this high, this close to 1, was a more rare occurrence when there was no linear relationship and would only happen less than 5% of the time to have this size of a R value, well, then that would be evidence in support of a linear correlation. So that's the logic. Okay, so they're showing the data values here. They gave us more than 5. They went up to what was it? 23. Doesn't look like 23 because there's another slide. All right, maybe those together get to 23. They're going to request possibly consider checking the requirements. So the first requirement of a simple random sample is questionable. They're saying we don't know how that came. The data are quantitative, but examining the original data does not appear that they're randomly selected pairs because this requirement is not satisfied. The results obtained may not be valid. So in this case, instead of just automatically checking all the requirements, they're saying, listen, we don't have evidence to support this. They may not be valid. We'll still follow through with the results, but until we confirm there was random selection here, this could not be valid. And maybe they just went to some particular chocolate-loving countries or something. So finally, we get a look at a scatter plot, and this is important. And you could kind of see, well, is this a linear pattern? If there's a sort of line going through the data here, there seems to be kind of a gap down here and here. Do these little outliers here throw it off? If those weren't there, it certainly would look a lot more like a linear correlation. So it says the second requirement of a scatter plot showing a straight line pattern is satisfied. They're saying this is good enough. This certainly, I think the R value will handle whether those two outliers are severe enough to throw the R value off. You let the measurement of R do that. But certainly there is nothing in the bottom right corner and the upper left corner, and the data does seem to kind of follow a somewhat linear pattern here. So they're saying, yeah, we're going to say this is satisfied. And again, your judgment will have to grow on this a little bit, but hopefully the problems will never be vague enough where you would get something wrong based on your judgment of the graph after looking at slides to develop your sense of things. So they're saying, all right, we're going to look at this and say that satisfies it. So now we have to use technology to compare the p-value to the alpha value. And if the p is low, that's going to support linear correlation. If the p is high, is not going to support linear correlation. So in this case, there's that R value, and they got a p-value in this case of like next to nothing. So they're saying if there was no correlation, the probability that our data would look as much like a line as that data does if there was really no linear correlation is practically zero. So in this case, it's showing us the stat disk display that a p-value is close to 0. So it's less than the 5% significance level. So we'd conclude there is sufficient evidence to support the conclusion that for countries, there's a linear correlation between chocolate consumption and the number of Nobel laureates. And so now they're talking about using a table and interpreting R with the critical value approach. You would look up the critical value on some table. So they've shown it to us here. There's the positive and negative critical value. And because our test statistic for R was larger in size than the critical values, then that is in support of the linear correlation claim. So they'd say we'd support that. So then finally, they sum up with some interpretation. If the computed linear correlation coefficient R lies in the left or right-hand tail region beyond the critical values, that supports there's a correlation, which it did in this case. If it had been closer to 0 instead, then that would not support it. And so they're reiterating that here because the figure shows that it was beyond those values, they support it. And that's their conclusion. Again, as before, I think the p-value method is more intuitive and speaks to the logic of the situation better than the critical value method, but they do have it here and they might ask you about it in a problem, so we definitely wanted to take a look at that. All right, so here is problem number 7 from homework number 13, our current homework of the week on 10.1 and 10.2. So it gives us a data set of matched pairs. It says use the given data set to complete parts A through C below. And notice there's no situation here. They're not talking about chocolate and Nobels or left and right hand. They're just saying X and Y. So this is purely, here's the numbers, practice doing some analysis. And so the first thing it asks us to do is construct a scatter plot. Choose the correct graph below. And look at these choices here. So here's clearly a negative linear correlation. Here's clearly a positive linear correlation. This looks pretty close to positive linear with a little bit of string at the end, maybe with an outlier. Maybe there's a curved pattern here. If it's this one, I really think it would be hard to tell. Here, there's a strong correlation, but it's clearly not linear. So that would be a case where you had a systematic deviation from a line, which would suggest a nonlinear correlation. But let's see which one is right. So I'm going to go to open the data in StatCrunch. And as usual, since these are matched pairs, we're going to see 2 columns where the n value is 11. And because we're going to make this graph, I'm going to go to graph. and we want to go to scatter plot. We have done this before, but that's where it is as a reminder. And I'm going to select for X the X and the Y for Y because they were nice and kept that simple. And that's it. I'm going to compute. So it looks pretty clearly that the D is the pattern here. So that's how you can take the data set, drop it in StatCrunch, go to Graph and make a scatter plot. We've actually done that before, but we will be doing more. So let's continue. Then it says, find the linear correlation coefficient R, then determine whether there's a sufficient evidence to support the claim of a linear correlation between the two variables. Well, that's interesting. So we're going to want to look at this carefully here. And here's where the logic I was discussing before is going to matter. Because notice, clearly from the scatter plot, there is not a linear correlation. There's a non-linear correlation. So the scatter plot will undermine any low p-value or high r value because the scatter plot is showing there is not a linear correlation here. There's a non-linear correlation. But nonetheless, we want to find out r. As we said, no matter whether there's a linear correlation or not, you can always calculate r with paired data values. So how do I do the r then? Let me just close up this graph. So we're going to go to stat. And when we're doing r distributions, we had other distributions before, we go to regression. Simple linear. So linear correlation coefficient means you're going to do a simple linear regression. So it's under the regression tab and you get simple linear. So again, we're going to pick the X and Y variables. And we could talk about a hypothesis, but the default's always going to work for us because our null is always going to be, they're separating the slope and the intercept, but for our purposes, the null is always going to be 0 and the alternative is always going to be not 0. So we never really have to mess with that happily, and we can just go compute. So now our little StatCrunch report has a little bit extra information in it. So we have to go through this for a second. So that they're at this point asking for the linear correlation coefficient. And so that's stated right here, R correlation coefficient. And then they give us the value right there. So that's, let's be clear because you might see T stat or an F stat and these other kind of things. But we're talking about the R value is right there. Now, I am going to also just point out they show a linear equation here as well. In 10.2, they're actually going to ask us for the linear equation sometimes, and we're going to be using that. So we're going to use this same tool in 10.2, and I've already shot an example of that as well. So just to let you know, this tool is useful for 10.1 and 10.2. All right, so having said that, we're going to get this to 3 decimals, which means I'm going to round the 5 up to a 6. So then it asks us to determine whether there's sufficient evidence to support the claim of a linear correlation between the two variables and to choose the correct answer below. And as I was saying before, there's 2 things you need to look at. You need to look at sort of the R value, the size of the R value, whether it passes the critical value or whether it produces a p-value that's below the significance level. That's one. And the other is you need to look at the scatter plot graph and see if it says there's a linear. You kind of need to do both of those things. But I'm going to point out that to give us distinct clarity, it says using the linear correlation coefficient found in the previous step, this 81%, use that to determine whether there's evidence to support the claim. So because they're focusing on the digital calculation of R here, not the graph, we, for the purpose of this problem, would ignore that the graph is telling us there's no linear correlation and just see if this passes, this test statistic passes the critical value. And how do we do what the critical value is for the 5% significance level? That's not given anywhere here. We don't have an R calculator. But as I mentioned earlier, they give us the table here. Click here to view the table of critical values So we have to use the table at the 5% significance level to see what the critical value of R would be. And then we have to use the R value we got and compare to determine if we have some evidence to support linear correlation. So let's look at the table. So luckily, it's pretty simple. It just lists the size of the sample, and it lists the significance levels 5% and 1%. And if you have a bigger sample and you don't have an exact value, like you have 42 and it jumps from 40 to 45, you would just pick the table value that's closest to the number of your sample. But in this case, we have 11 in our sample size, and that is exactly on the table. And at the 5% level, we have 0.602. So the critical value, positive or negative, would be 0.602. And we got beyond that, closer to 1, we got 0.816. So because that's bigger than the 0.602, that would support there's a linear correlation. That side of the calculations supports a claim of a linear correlation. So I need to choose that. There's sufficient evidence to support the claim of a linear correlation. Again, that's using the linear correlation coefficient found, not using the scatter plot graph. All right, so then we say, oh, well, it's giving us the wrong answer. The scatter plot shows it's wrong, but they have finally a part C. It says, identify the feature of the data that would be missed if part B was completed without constructing the scatter plot. So they're trying to show you that, yes, you might look like there's a linear correlation. If you just look at R, you need to look at the scatter plot too. And then what we saw in the scatter plot is there was a non-linear curved kind of correlation. So the scatter plot reveals a distinct pattern that is not a straight line pattern. That's the key that would be missed if we just looked at the StatCrunch numbers and looked at the R value and stuff like that.